Now, since I got this picture here, I've got small pictures here. What I'm trying to depict here is you got a z-axis, an x-axis, a y-axis. You've got a dipole sitting on the y-axis, oriented along the y-axis. You have a coil here. Think of the Hemlhotz coil, one of the loops of the Hemlhotz coils. It's difficult to draw this in 3 dimensions, and my drawing skills are limited. So we imagine just rotating this plane so that we're viewing it right along the y-axis, and here it is. And here is the side view of the coil, the Hemlhotz, the loop. And here's your dipole. And here's your dipole field lines. Here are your dipole field lines. Your dipole field along these lines at the position of the coils is going to be strongest here, and then a little less strong here, a little less strong here, quite a bit less strong here, and of very little strength anywhere else. So we have something much like this. So to impose this somewhere else in my picture, here's our cross section, and here's the way the field might cut the coils. We integrate the field, integrating the normal component of the field, the component of the field perpendicular to the plane, and we could indicate the normal components of these vectors. So that we can get the total flux. This would correspond to a magnet. Actually, let me grab a magnet. Like so. Now the magnet isn't a single dipole. The magnet can be thought of as an infinite number of infinitesimal dipoles. And you know, one thing I didn't do, I didn't zoom the camera. Maybe you can see a little better now. Okay. Again, an infinite number of infinitesimal dipoles oriented in this direction. Okay, now the coils are quite a bit bigger than the magnet, so all these dipoles are pretty much not too much further from one part of the circle than the other. So we can kind of model this as just a single dipole, but of course the geometry of it's going to be a little bit different than a uniform dipole. Still, the general picture is still going to be much like this. If I switch this dipole, or this magnet, this way, the dipoles now all face in this direction. So if I reverse this picture, then the integral of these perpendicular components is going to reverse sign. So that whatever the magnitude of the total flux through the surface was here, the change in the flux is going to be double the magnitude of this flux. We're going to go from either a positive flux to a negative, or maybe a negative flux to a positive. And again, if you go from a positive quantity to an equal and opposite quantity, the magnitude of the change is double that quantity. So I'm not going to try to draw that, but you can imagine if I reverse this thing, all these arrows go the other way. The flux goes in the opposite direction. Now we have conventions for the positive and negative directions. So with these orientations, this would correspond to a positive flux. Reverse the vectors, it would be a negative flux. So the dipole reverses, the magnitude of change of the flux will be double the magnitude of the flux. And the magnitude of change of flux over delta T will be double the magnitude of the flux. And your electric field, well, your potential difference at any instant is the rate of change of your flux with respect to time. The electric field is the circumference of the loop divided into the voltage, okay? Voltage divided by length. And I don't know why I put a delta in front of the V. Your voltage at any instant is this. Your average voltage is going to be this divided by your delta T, and so forth. So, there's the picture, the flux picture with the Hemlhotz coils. If you have a big old Hemlhotz coil here with a big picture of the field, okay? So the coil's in this plane, big old loop, 10 feet around or whatever. And the loop is, let's say, right here on this side of the dipole. If you reverse the dipole, we see that all the vectors are going to reverse. Total flux is going to reverse, and we get a picture that's consistent with all of this.